All right, guys, can you guys hear me? Hey guys, can you guys hear me?
Yes.
All right, so in that case, we can get started. Hey guys, welcome to our bootcamp. So as a common practice, whenever we're approaching the AMC or the Euclid math competition, we're going to have a bootcamp. We're going to use 10 lectures, try to cover the most important concepts for the upcoming math competition, trying to give you guys a summary for the most important concepts, the most classic, the most, what should I say, the mainstream problems you're going to be seeing in the math competition, giving you guys a little bit idea how to expedite your solution process, pretty much like a kind of a bootcamp that you were normally expecting for most of the math competition courses. So today is our lecture number 1, and we're going to cover the 2D geometry. Okay. So before we get started, here's a quick recap of what we will be covering in these 10 lectures I'm going to give you here. So this is like the syllabus, right? So for the left-hand side is our AMC12. The right-hand side is our AMC10. Today's lecture is for AMC12. We're going to be using 10 lectures covering the most important 10 topics in the math competition. We're going to start it with the 2D geometry. Next one is going to be 3D geometry. And then we're going to go to the Coordin geometry. So basically, we're going to use the first 3 lectures talking about all the geometry-related concepts. And moving forward, we're going to be using 3 lectures talking about the algebra. Algebra is more like a smoothie. It has like so much information. Pretty much everyone learned algebra as the very beginning of their math journey, right? So we're going to cover the functions, equations, inequality. We're going to talk about the sequence, the exponential function, logarithm function. We're going to talk about the most important, the trigonometry, complex number, polynomial. Especially, I think algebra 3 is kind of like, especially for AMC 12. If you go for AMC 10, it won't ask you too much about the trigonometry, complex number, polynomial, so on and so forth. And moving forward, we're going to use 2 lectures talking about the counting and the probability. And the last 2 lectures talking about number theory. It's kind of like, I think it's a well-defined lecture. We cover the most important concepts for the math competition. And hopefully our 10 lectures can work as a kind of like a snapshot. You guys, the most important thinking process, the concepts that you have to know in order to go to the math competition. All right, this is the very beginning, just kind of a quick recap. So if all good, let's fly to our today's lecture. Today's lecture is going to be our lecture number 1. We're going to be talking about lecture 1, 2D geometry. Okay, so as a common practice, before we jump to all the problems, we'd really like to give you guys a short and brief overview. What are the most important concepts that you have to know in order to go to the math competition? All right, so talking about the 2D geometry, we always get started with the triangles, right? Triangle is considered to be the foundation of the 2D geometry. So talking about the triangle, the most important thing I want to say is that there are actually some intrinsic inequality relationship in a triangle. We want to use the word intrinsic because these has nothing to do with the special type of triangle, can be acute, obtuse, right, whatever. But there are some intrinsic inequality relationships in a triangle. The first important one is actually what we call the triangle inequality, right? As long as you have 3 sizes, there's a relationship between the 3 sizes. Everyone knows that. And actually, you have a scalar form here and also a vector form. The vector form goes like this, right? If you take the 3 sizes as 3 vectors, right? One is x vector, the other is y vector. So the third one will be considered x vector plus y vector, right? So you can basically use 2 forms to understand the same thing, right? So this is the number 1 important stuff. And then the number 2 important stuff, as long as I give you a triangle, there's another very important intrinsic inequality that is going to be introduced by triangle in triangle's trigonometry. For instance, you have an angle named theta, right? So of course, your sine theta is going to be from 0 to 1. and your cosine theta absolute value also going to be 0 to 1, right? So that being said, in the future, as long as you're given a triangle without any extra information, so without further ado, you need to basically have these two very important relationship pop up automatically, and that's going to help you solve a lot of problems. Okay, that's the first one, the triangles inequality. So moving forward, the second part is like a given. As long as you went to elementary school, you'll be able to know this, the Pythagorean theorem, right? For a right triangle, the three sides have such a perfect square relationship. Well, most of the time in math competition, instead of giving you three sides, so let's say this is a right triangle, right? I give you side A, I give you side B, ask you to determine what is the side C. This is very kind of like a direct thinking process. But most of the time in math competition, they will do it reversely. The question is going to give you three sizes of a triangle. And for some reason, these three sizes happen to be the three sizes of a right triangle. So therefore, you need to remember what we call a Pythagorean triple, aka as long as you see three sizes of a triangle, you should be able to determine, okay, this is a right triangle, okay? So if we do a quick analysis in the last 20 years of the math competition, you're going to find out these 2, 3, 4, 5. So these 5 Pythagorean triples are actually very popular. For some reason, AMC love to test you from time to time, just basically on these 5 Pythagorean triples. So like I said, most of the time, it won't really give you the right triangle, ask you to do the Pythagorean triple. However, it should be the other way around. They give you a triangle, or maybe, sometimes they just give you a random shape, whatever. And then during the calculation process, you happen to find out what's the value for this. What's the value for this? What's the value for this, right? They're not given right away. It's actually during the calculation process. Then you need to do the reverse engineering as long as you see, okay, three sizes from a triangle, they fall into such a Pythagorean triple, you can determine right away, this is actually a right triangle. Okay, this is actually where we come from. Okay, now this is the second part. Moving forward, let's go to the third part. The third part is the famous angle bisector theorem. So trust me, this is extremely important, and AMC love to test you almost like every single year. As long as you have a triangle, you have an angle bisector. Of course, this is angle 1, this is angle 2, right? Your first reaction is angle 1 equals angle 2, but trust me, they don't really test you the angle thing too much. Well, more often than ever, they will test you the side relationship, aka the angle bisector theorem. So for instance, this guy AD is an angle bisector, then automatically you're going to have BD over DC will be equals to AB over AC, right? An angle bisector is going to cut the opposite side of the triangle into two parts, and the proportional between this proportion between these two parts will be equals to the two sides ratio. So trust me, this is extremely important, especially if you want to go to AIME, you can find out angle bisector plus the Menelaus theorem. These two theorems always take roughly question number 5 to question number 7 a lot. From time to time, if you see a geometry problem roughly in number 5 and number 7 in AIME, you will actually find out using Menelaus plus angle bisector very often. Just try to bear in mind, this is like a summary that we find out in the math competition. All right, so let's continue. Moving forward, number 4, we're going to talk about the important Stewart theorem. Okay, Stewart theorem is actually a very important and also very intrinsic theorem for pretty much all the triangles. Again, this theorem has nothing to do with the type of triangle. You don't really have to give me any extra information. As long as you give me a triangle, within this triangle, you pick up one side, let's say side ACB, you make a line, you'll find a point D, make a connection, then you're going to have 1, 2, 3, 4, 5, right? You have 5 segments. This is quite understandable, right? Okay, as long as you have 5 segments, then you will be able to find out actually there's a good relationship between these 5 segments. So what's the relationship? M times A. A actually means M plus N, right? I'm going to highlight it here. M plus N. Then times N plus D times A times D equals to B times M times B plus C plus N plus times C. C times N times C. So that being said, as long as you give me a triangle, okay, in this triangle, you find a random point in the BC side or like whatever. So there will be an intrinsic relationship between these 5 segments. So as long as you know 4, okay, you will be able to determine the last one. Is it right? So this is actually a very important theorem. So sometimes if you get lost with some complicated problems, so on and so forth, so try to use this very basic theorem. That's going to really help you out in a lot of scenarios. So try to remember this. And how to remember this? There's a very easy shortcut. You can use a man and his dad put a bomb in the sink. A man and his dad put a bomb in the sink. This is a very typical way how you can remember this Stewart theorem. Okay, so moving forward, some students say, hey, I really can't remember this. This is like too complicated. In that case, you know what? You can actually try to remember some specific scenarios. Instead of remember like the big one for the very generic scenario, try to remember some specific scenario. For instance, what if AD is not a random segment, AD is the angle bisector. So that being said, this is going to be an angle bisector theorem. Angle bisector length theorem. Okay? You will be able to determine the length of an angle bisector. So AD square equals to AB, AC minus BD, DC. You see, this one is much straightforward, right? Much more straightforward compared with the original generic form. Well, the other part is, what about AD? AD is no longer angle bisector. AD becomes the median of BC. Median is also considered to be a special scenario, right? So this, we're going to have what we call the median length theorem. Median length theorem will be 4AD square, 2AB square, plus 2AC square minus BC square. Okay? Last but not least, what about you have AB equals AC? So that being said, you're looking at a isosceles triangle, right? At this moment, AD can be any random guys, but AB has to be equal with AC. So that being said, you're going to have AD square equals to AB square minus BD times DC. You see, the Stewart theorem is actually a very generic theorem. If you can't remember Stewart, no worries. You can try to take care of this like specific scenarios, right? Try to enrich the condition, give a little bit more conditions to the Stewart, and moving forward, you'll be able to have this 1, 2, 3 different, what we call like a length calculation theorem, whatever, can be an angle bisector length, can be a medium length, can be a random line within the bottom of your isosceles triangle. So this is also considered to be a very important specific scenario that you need to remember. Okay? All right, if all good, let's continue. Number 5, we're going to talk about the centroid of a triangle. Actually, in our regular lectures, we spend a lot of time talking about the different centers in the triangle, right? Some centers can have much flowery properties than the others, right? Most important 4 centers could be the incenter, circumcenter, centroid, and orthocenter, right? This is what we said in our regular lecture. However, within these 4 centers, I think the centroid is the most important thing. And AMC love to test you from time to time. So that means that I actually extract out the centroid. There are two very important properties for the centroid. The first one is the centroid actually cut the median into 2-to-1 part. This is extremely important. Try to prove this, you can use the congruent triangle, so on and so forth. So let's say for this guy, it's going to be a 2-to-1 relationship. This is also 2-to-1. This is also 2-to-1, right? The reason I use different color means these twos, the blue two, the red two, the black two, they're not the same. However, this line, this median per se, will be cut into 2-to-1 proportion, right? This is extremely important. Sometimes, for instance, if you see 2018 AMC12B, question number 13. So that problem looks like a little bit drowsy. However, if you know this, you'll be able to solve the problem in no time. Okay? And also how to determine what is called the coordinate of the centroid if the 3, 1, 2, 3 vertices are given with all the coordinates. So to determine the coordinate of the centroid is actually very straightforward. You just basically add the 3x coordinates together divided by 3 and add the 3y coordinates together divided by 3, right? So that means that you'll be able to determine the coordinate of your centroid. Centroid, we also call it is the mass center, right? So basically, if you put a kind of like if you use your finger, you put a finger poking that centroid, you'll be able to basically balance for that triangle. Okay? So this is actually something very important, and they like to test you from time to time. So moving forward, number 6 is going to be the congruent triangle, which is very important. So try to determine two triangles are congruent. There are several determination rules. I'm pretty much sure you guys already know that from day one. One thing I like to highlight is that regardless of whatever rule you want to use, to determine two triangles are congruent, you at least need a side information. You can't just use angle to determine two triangles are congruent. They must have a side information in your determination rule. So you can have the 3 sizes, 2 sides and their included angle, 2 angles and their included side. Angle, angle, side means one angle and the other angle's opposite side, right? And for the right triangle, as long as you know 2 sizes, you're good. Because the right triangle, you have a Pythagorean relationship. As long as 2 sizes are the same, the third one will be automatically the same, right? Using the Pythagorean relationship. Well, the only thing I want to mention here is that SSA is not sufficient, right? This is not a sufficient determination rule to see two triangles that are congruent to each other, because you can easily find out, let's say, this is my first triangle. It has side length 11, side length 11. They're sharing 30 degrees. And then the other side here is actually 6. Well, you can actually generate two triangles that are both having 6 as one of their side, right? However, the shape of these two triangles are totally different. One is an acute triangle, the other one is obtuse triangle. So that being said, SSA is not always guaranteed because it could generate two triangles that are they're basically meeting the same condition, right? But one thing I want to mention is that, even though you have two triangles, one is actually acute triangle, the other one is obtuse triangle, right? So even though you have two triangles, but if you just want to focus on this original acute triangle, let's say, if your original triangle on the left is acute, so the right triangle, the acute one, should also be congruent to the left one. Or alternatively, if your original triangle is an obtuse triangle and you generate a new obtuse triangle, these two obtuse triangles are still congruent. So that being said, even though this is not a determination rule, but I don't want you guys to totally abandon it. So this one also gives us a way to determine two triangles are congruent. However, to figure out, you're going to have two possible scenarios, obtuse and acute. As long as in the determination process, you can eliminate one of them, Let's say based on your calculation, your proving process, you can prove the right-hand side triangle is definitely acute triangle. The left-hand side is also acute triangle. So that being said, there's no way to be so worried about it. You don't have to say, okay, this is like two things I won't be able to determine. Not really. Okay, so the reason I put it here is because it generates two types of triangles. For sure, obtuse and acute, they won't be congruent to each other. But as long as you can confirm one thing can be eliminated, you can be more than brave to use this determination rule. So I hope you understand. This is the reason where we come from. All right. So moving forward, after we finish the congruency, we went to the similarity, right? The similarity rule is actually more casual compared with the congruency rule. Like I said, congruency, you must have a side. But similarity, not really. You can just have angles, or you can have some angles, some sides, or you can only have sides, right? So that being said, because the congruent triangle is more strict condition, two triangles must be exactly the same to be considered as congruency. But similarity is more casual, right? Two triangles, they're just alike, and they will be considered to be similar, right? Alike, and then that's it. So a quick recap of what we need to do for the similarity. You can have AA, two angles. You can have two sizes and their included angles. You can have three sizes. Actually, if you go to our regular lecture, we already introduced there are 12 different ways how to determine two triangles that are congruent. We talk about, like the swallow shape, the X shape, the A shape, right? And some hybrid shapes, so on and so forth. So here we don't like to unfold too much, but generally speaking, there are a lot of common patterns you need to remember before you can determine two triangles that are similar. Okay, and AMC is actually, what should I say, from time to time, testing you this common patterns. And the more pattern you know, the faster you'll be able to determine two triangles' nature, being congruency, being similarity, so on and so forth. All right. So moving forward, number 8 and number 9, these are the two twin brothers, what we call always like the important ratio theorems within the triangle. One is the Menelaus, the other one is the Sivar. These two theorems are actually just like a twin brother. They always like to test you from time to time. So for the Menelaus, what you need to do is that you need to have a triangle, ABC, right? I'm gonna highlight it here. You're gonna have a triangle ABC. And within this triangle, the most important thing is you need to have a transversal line, okay? The transversal line cut the triangle into two parts and also intersect with one of the extension, okay? As long as you have this, then you will have such a relationship. That's gonna be your PB, CP, QC, QA, AR, RB. It's pretty much you start from one vertex, right? All the way go to the transversal line intersection point, and then go to another vertex, go to another intersection point, another vertex, another intersection point, and then go back to the original vertex. You basically take a circle for this triangle based on the three intersection points, right? So this is actually an intrinsic property for any triangle. It has nothing to do with the special type of the triangle. You give me a triangle, you will be able to have such a relationship right away. Okay? So this is the very important Menelaus. Actually, if you go to the AMC and AIME, like I said, AMC might not test this part very often, but AIME definitely, like I said, AIME question number around number 5, number 7, number 8, they love to test this from time to time. It is very important. Okay. The other part is like the Sivar. Sivar is also pretty much the same thing. As long as you have any kind of triangle, you have a dynamic point in the middle, and then you make some connection to this dynamic point, do the extension to intersect with the three sizes, then you'll be able to have something like this. BD, DC, CE, EA, AF, FB. Take a circle, you'll be able to have such a relationship. Very understandable, right? All right, so that being said, we finished the most important two generic ratio theorems within the triangle. All right, moving forward, next part, we're going to talk about the sine law and cosine law. Trust me, these two laws are so important, especially cosine law. Cosine law will be tested every single year, no exception, every year. No exception, and they will be tested all over the places. It's not only one question, two questions. It's going to be all over the places. If you go to the math competition, you're going to see the solution manual. You will be able to see cosine law all over the places. Okay, so sine law is fairly easy. Side over the sinusoidal value of the opposite angle, right? And then you'll be able to have this 2r. That's it. And cosine law. Cosine law is the most important law that build up the relationship between the side and the angle. For instance, see cosine A, right, could be equals b squared c squared minus a squared to bc, right? Okay, this is one of the cosine law for cosine A. You see, the left-hand side is only angle. The right-hand side is only side. You see, angle and side. So that being said, cosine law is the only one law that 100% segregate the angle and the law. And also, you can only use the law relationship to determine the angle relationship and vice versa. You see, sine law, you need the two angles, right? The two angle proportion is going to be the same as two side proportion. However, cosine law, you can just give me side. I'll be able to generate the angle just based on side. So that being said, it's very interesting that the sine law is actually a combine between sides and angles. However, the cosine law is very strong. It can 100% segregate the angle and the side. Just use the side to determine the angle. This is actually extremely important property. And from time to time, if the question gives you a bunch of side, and then at the end of the day, ask you to determine an angle, the no-brainer, it must be the cosine law. At least cosine law must be highly involved in the calculation process. All right. So that being said, we actually wraps up the most important concepts for the triangle. So like I said, triangle is actually a very important prototype for your 2D geometry. As long as you go to quadrilateral, you go to even more, right? You go to pentagon, you go to hexagon, so on and so forth. One of the most important strategy is try to cut the complicated polygons into different triangles. Sometimes you can't really do the problem at a very high vision, big polygons, but cut it into small triangles, you will be able to solve the problem fairly quick. So always keep in mind, triangle is your prototype for pretty much everything. All right, moving forward, let's go to the circle part, right? Circle is actually a very important part for the 2D geometry as well. So talking about the circle, of course, we get started with the basic definition, the tangent, the secant, the distance, blah, blah, blah. These are so easy. And one of the most important thing I want to say is the power of a point, right? So power of a point is not one theorem, it's actually a series of theorems that actually contains three. The first one is what we call a chord theorem, right? If you have two chords intersecting with each other within a circle, you're going to have DE times EB equals to AE times EC, right? And the two chord here times here equals to here times here. Okay. Second is the tangent secant theorem, right? If you have a point which is outside a circle, you want to make a tangent, you want to make a secant, then automatically you have AB squared equals to BC times BD, right? This is what we call the tangent secant theorem. And then if your tangent is getting a little bit closer to the circle, right, the tangent degrades into a secant as well, you're going to have your secant theorem. Secant theorem is actually your CB times CA equals CD times CE, right? This is something quite important that you need to remember. One more thing we like to have a quick discussion is in your math competition, as long as you see tangent, what are you going to do? Right? Because I think tangent is actually a very important thing you're going to see from time to time. As long as you see tangent, actually, there are three important prototype that you need to remember. The first one is you see a circle and you see a tangent line. Just one circle and one tangent line. Then your first conditional react is try to do a connection between the circle center to the tangent foot, because automatically you're going to have a 90 degree, right? Your radius will be perpendicular to the tangent line. Second and the third, I think, is actually more often. One is that as long as you have two circles, they're tangent to each other, they're exterior tangent to each other. As long as you see this, there are two important conditional react that you have to do. One is fairly the same. You do a tangent line, right? So if you do a connection between these two circle centers, the tangent line will be perpendicular to your circle centers connection, which makes sense, right? Well, there's another one which is way more important. I like you guys to remember is when you have a here, right? So this time what you can do is do a connection between these two circle centers and make a common tangent line. Okay, a common tangent line, because these two circles that are externally tangent to each other, it is quite easy for you to create a common tangent line. And then what you have to do is you're going to do a connection between these two, okay? Pretty much the same thing, right? Because this is the same coming from here. As long as you have a line tangent to a circle, do a connection between the circle center to the tangent line. Okay, now if I zoom out a little bit, what you can do is that you can actually make a perpendicular line from the relatively smaller circle to the bigger circle's radius. Let's say this one has a radius r, this one's a small r, this is small r, this is a big R. So this part is going to be what? This part is going to be the big R minus the small r, right? You just basically do a projection, right? Making the small circle to the big circle. So that being said, let's have a focus on this triangle. This is a right triangle, right? This little right triangle, you're going to have something like this. This is 90 degrees. This is big R plus small r. This is big R minus small r. Then using your Pythagorean theorem, you will be able to determine this is 2 under root big R times small r. And what is that? And this is actually the length of your common tangent line, right? This is exactly the same thing, 2 under root big R small r. So that being said, if you check the math competition from time to time, AMC10 or AMC12, as long as you see two circles that are externally tangent to each other within such a relationship, try to work on this magic triangle. This little magic triangle is really going to help you to do a lot of calculations and help you to expedite your calculation process. All right? This is actually one of the type. You have two circles externally tangent to each other. You can also have them internally tangent to each other, right? Which makes sense. The internal one is fairly straightforward. You also want to do a common tangent line and do a connection between the two circle centers all the way to this. You'll be able to find out two circle centers, make a connection, will be perpendicular to this common tangent line. Okay? These are the most important thing I want to say. And moving forward to number 12, I want to talk something about the cyclic quadrilateral, because from time to time, AMC love to test you the cyclic quadrilateral. Okay, a triangle. Okay, of course, a triangle could be inserted into a circle, but not all the quadrilaterals could be inserted into a circle, right? There's only certain type of quadrilaterals should have a common circle. We give a name, the cyclic quadrilateral. So what kind of quadrilateral will be a cyclic quadrilateral? Or what kind of property that a cyclic quadrilateral could have. The first one is if a quadrilateral is cyclic, the opposite two angles will be supplementary. The two green ones plus the two red ones, the both equals to 180 degrees. And this is actually a necessary and sufficient condition. As long as you have a quadrilateral which is cyclic, you're going to have such a property. And also, as long as you have a quadrilateral has such a property, then you can claim this is actually a cyclic quadrilateral. Okay? The second part is actually, you see, some angles are the same. Let's say ABD is this angle. ACD is this angle. They are the same in measurement because they're actually facing the same arc, AD, right? The same arc actually gives you the same angle. And this is actually also sufficient and a necessary condition. As long as I give you a triangle, as long as I give you a quadrilateral, I can say this angle is the same as this angle, then you can claim this quadrilateral is going to be a cyclic quadrilateral. So pretty much all the properties from the cyclic is sufficient and a necessary condition. Okay. Moving forward, how to determine the area of a cyclic quadrilateral? You have a shortcut way. You can basically say if the four sizes is A, B, C, D, try to determine S is the half of A plus B plus C plus D, then the area of this cyclic quadrilateral could be written in such a way. Okay, so this is only good for the cyclic quadrilateral. If you give a random quadrilateral, you can't do this. And this is quite like the Heron's formula, right? Heron's formula is something quite similar, right? P equals to the S minus A, B, C, right? P is equal to A plus B plus C, Heron's formula ABC, right? Because Heron's formula is for triangle. Triangle can definitely be inserted into a circle, then you can use such a fashion. So a quadrilateral, as long as you can insert this quadrilateral into a circle, then you have something quite similar. You see, most of the time, this math competition concepts are very alike, right? Whatever you got from triangle could be easily transferred into a quadrilateral, into even more polygons. Okay. Moving forward, number 13 is extremely important problem, extremely important theorem, that is the Ptolemy theorem. As long as you have a quadrilateral which is cyclic, then you will be able to have such a relationship. AC, BD, AC, BD, the multiple of two diagonals is actually equal to what? AB, CD, plus BC, AD. So the sum of the product of two opposite sides actually equals to the product of two diagonals, right? The sum of the product of two opposite sides is actually equal to the product of two diagonals. This is good for a cyclic triangle, a cyclic quadrilateral, and also this is sufficient and necessary. If you give me a quadrilateral, you can find out such a relationship. Okay, this quadrilateral is going to be a cyclic quadrilateral. So you see, like I said, pretty much all those kind of cyclic quadrilateral related properties, they are back and forth, sufficient and necessary condition. All right? If all good, let's continue. Number 14, we like to talk about something about the area of a triangle. If you went to our regular lectures, you see, we're going to spend almost like 2 lectures talking about the area method, because area is like so much important in the math competition. Also, they actually did a quick calculation. They said 70% of all the AMC, AIME, geometry problem, they're all getting involved into this algebra, into this area calculation. Might not every single problem ask you to determine the area, but in the solution process, you're actually getting involved how to determine the area, from the area, how to determine certain segments or certain angle, so on and so forth. So that being said, we like to have a quick summary about the most important things, how you can determine the area of a given triangle. So the first one is the definition, right? So there's nothing to say. You have a height, you have a bottom, right? And then multiply them, divided by 2, you'll be able to determine the area of your triangle. You know this, you can graduate from elementary school. The second part is the Heron's formula. We just talked about it, right? Heron's formula is determined as long as I have 3 sizes of my triangle, then without really go to how to determine the age, how to determine the angle, blah, 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 you will be able to directly determine the area of this triangle, right? Using the 3 sizes, you can use the Heron's formula, directly determine the area of the triangle. Number 3 is the important shoelace. Shoelace is actually more for coordinate geometry, but I think it's always important that we like to bring it up. In the XY coordinate, if I give you 3 points with all the vertices, okay, so you'll be able to determine the triangle for sure, right? So now this triangle is actually have the 3 vertices. And as long as you know the coordinate of the 3 vertices, it's actually fairly easy for you to determine the area of this triangle without going for a very complicated calculation process. And what is the formula you need to remember? And this is the formula, okay? As long as you know the 3 vertex of a triangle, the coordinate of the 3 vertex of a triangle, you can easily determine the area of this triangle without having to list out the side, the distance, the height, so on and so forth. You can just go for a very straightforward process and you get pretty much everything you need. Okay, this is actually a very important theorem, trust me. From time to time, they will be able to really help you to expedite your calculation process. And this is only for the triangle, right? Actually, you can make it more generic. Not only a triangle, any kind of like, you know, like the convex is the word. Any kind of convex polygon, as long as you have all the, I'm going to give you this, A1, A2, all the way to AN, okay? As long as you have the coordinates for each of this vertex, then you'll be able to determine the area of such a convex. So this is important thing. It's a convex polygon. If you have a convey, you can't do that, right? But the good part is most of our high school math competition courses are just focused on the convex polygon, okay? As long as you know every single coordinate, every single vertex coordinate, then you can basically put it here into this big formula and you can determine the area of the shape right away. Okay. And besides that, you can also try to use some trigonometry to determine the area. You know, something like this, right? If you have like a triangle, this triangle has 2 sizes, here, here, and you know this included angle C. So the area of this triangle could be 1 over 2, A times B sine C, which is quite understandable, right? And last but not least, this is also very important. As long as you have a triangle, and this triangle, you know something about the yin circle or like the circumcircle, you know the radius between these 2 circles, it can also help you to expedite your calculation process. Let's say if I have a triangle here, I know the triangle has a yin-squared circle. The radius of the yin-squared circle is r. So the area of this triangle could be written as r times s. S is the semi-perimeter. A plus B plus C divided by 2. This is for the yin-squared circle. Then what about a circumcircle? If I know a triangle has a circumcircle, circumcircle's radius is r, also 3 sizes ABC, the area could be written as ABC over 4r. So trust me, these 2 things, you might not use them very, very often, every single time, but from time to time, as long as you see some problems, you can use this. It can really help you to expedite your calculation process. All right, I think that's pretty much what I want to say for the first part. The most important concepts that you need to know in order to go to the AMC12/AIME math competition. Any questions for me? Are we all good? So far, it's all good? Okay, perfect. If all good, let's go to our second part. All our lectures are broken into 3 parts. The first part, the concepts. The second part is I want to give you some summary about the important type of questions. Okay? In the math competition, especially AMC12 and AIME, talking about the 2D geometries, normally speaking, we're talking about 4 major types of problems. 1, 2, 3, 4. The first part is basically using some important theorems. Okay, so this problem is going to test you some very important theorems for the 2D geometry. And the 2 things are very often, one is the cosine law. And the other one is the famous angle bisector. So trust me, even the angle bisector is more important than cosine law, because as long as you see the angle bisector, trust me, 100%, I can always say that, you're going to use the angle bisector theorem. Today, we're going to give you some problems from AMC12, from AIME. You'll be able to see how we can utilize them in the real math competition. Important theorems. Second is whenever you see the similar triangle, most of the time, they will test you a very, very important property is the area ratio is actually equals to the similarity ratios for a fixed square. Okay? As long as you see similar triangles, from time to time, as long as the question asks you something about the area, if you can remember, like I said, most of the time area is probably going to take 70% of this entire 2D geometry. So as long as you see similar triangle or some similar shapes, not really triangle, could be any kind of similar shapes, the similarities ratio, take a perfect square equals to the area ratio. This is so important, and they test you every single time. The third one is that sometimes when you try to do some 2D geometry problems using a direct way, a direct algebra and the geometry way could be a little bit challenging. Alternatively, if you can use the help of some of the trigonometry, you can really help to expedite your calculation process. So this problem sometimes might be a little bit challenging because you need to be familiar with all the trigonometry formulas, so on and so forth. But just try to bear in mind for some relatively difficult problem or relatively heavy calculation problem, if you can use the trigonometry, it's really going to help you to save a lot of time. Today, we're going to give you some sample problem for that as well. And last but not least, is whenever you're dealing with circles, instead of having those basic concepts, always bear in mind, try to use the cyclic and Ptolemy theorem. These 2 theorems can always help you to expedite your calculation. Yeah, of course, you can solve the problem using the regular similarity, congruency, blah, blah, blah. But as long as you do the problem using the cyclic, using the Ptolemy, it can really save you a lot of time. So in today's lecture, we're going to give you some sample problems. You can have a look at it, how I can use these tricks, these 2 problems, these 2 theorems, try to expedite this entire process. So generally speaking, there are 4 major problems we're looking at for the 2D geometry, and I have already listed them out here. Okay? Any questions? So far, so good? Yeah, if you have any questions, you can just let me know. We just want to have more interactions with the students. All right, if all good, I think let's go for like the real, like the real stuff, right? The beef and potatoes. Let's try to give you some problems to cover each of this category. I'm going to show you guys the most important thing is the thinking process. How to think as long as you see all those problems. What are the conditional react, I keep saying these two words, the conditional react is going to guide you to solve the problem. We're not reading the answers for you, right? The most important thing, I like to guide you to think how you can think in order to have the correct answer. All right, so if all good, let's go to our category number 3. Let's go to some real problems. Okay, let's go to our category number 1, right? Category number 1, like I said, some important theorems, especially I want to say the angle bisector. It is like so important. All right, so let's go to our first problem. Okay, our first problem is a problem that comes from 2013 AMC 12B, question number 24. We'll always give you guys some relatively difficult problem, try to guide you guys the thinking process. So a problem says, let ABC be a triangle where M is the mid of AC. You have to highlight this mid, right? Mid is important. CN is the angle bisector. Okay, angle bisector. Highlight that. As long as you see the angle bisector, you're going to use the angle bisector theorem. No-brainer. Of ACB with N on the AB side. Let X be the intersection of the median. Okay, I see a median BM and the bisector CN. CN is bisector, we just mentioned that. And the triangle BXN is equilateral. Okay, equilateral is a very strong condition, right? Equilateral means it has the same angle, the same side, pretty much everything is the same. With AC equals to 2, what is the measurement for BX square? For most of the geometry problem, no, pretty much all the geometry problem, the most important thing is you need to have a good graph, right? If you do not have a good graph, there's no way for you to solve a geometry problem. Okay, so let's go for a nice graph. You have something like this. I'm going to highlight it here. You have a triangle. The triangle have a median here, have an angle bisector here. Something like that. Okay, I'm going to give you guys all the important denotations. A, B, C, M, N, X. Okay, so ABC is a triangle. M is the mid. Okay, M is the mid. I'm going to highlight it here. And AC, a mid of AC, right? CN is the angle bisector. Angle bisector means these two guys are the same. X is the intersection, blah, blah, blah. If AC equals to 2, AC equals to 2 means this is 1, right? And we know this guy is an equilateral triangle. Okay, my graph is not 100% nice, but you get an idea. Okay, so what's the value for BX square? What's the value for BX square? How can I determine the value for BX square? Well, to determine the value for BX square, basically you need to determine one of the sides of your green triangle, right? That's basically where it comes from. Well, I have no idea how to do that, but I think there are some very important conditional react you have to remember. So this problem actually can use a lot of conditional react. First thing first, as long as you see such a shape in our regular lecture, we have already shown you guys, sometimes if you see such a shape, if you can figure out these two angles are the same, then automatically you have this triangle would be similar to this entire black triangle, right? Because they're sharing the same side. They're sharing the same angle here. If you can have these two green dot angles are the same, then you have these two triangles are similar to each other. This is like a very important pattern, conditional react within our 12 different patterns, right? Okay. Is it possible? I'm not so sure. I really have no idea. Is it possible these two angles are the same? Is it even possible these two angles are the same? Who can tell me? I don't even know. It might be possible. It might not be possible, but this is only a very big thing. Yes, go ahead.
As for the angle BXC, actually it's not, let's say, angle for the angle BXC and angle BCX, as for the angle XBC is a model, and then add them all together is going to be like 180 degrees. And for another triangle, which is supposed to be ACN, they're actually two identical angles together. So the A and C will be 120 degrees as well. So
Exactly, right? That's pretty much a very nice explanation process. Actually, you can find it out. Yeah, please help me to mute yourself as long as you're after your talk. Yeah, it will be easier for pretty much everyone to follow. Thank you. Yes, I think this is right. You can do a very quick exterior angle stuff because if I check this exterior angle, 60 degrees equals to angle 2 plus angle x plus angle, I'll say, blue x. Okay? And similarly, this 60 degrees equals to angle 1 plus this angle blue x. These two blue x's are the same. So therefore, you have angle 2 equals to angle 1. Like I said, right? I don't really know how to do this problem, but I see all these patterns. I'm going to use my conditional react. So maybe my conditional react is going to help me to do some problem. So that's the process. Okay, as long as you have this, okay, these two triangles, they're indeed similar to each other. So triangle BMC is similar to triangle ABC. As long as you have two triangles are similar to each other, automatically you have this proportional relationship, right? BC over MC equals to AC over BC, aka...
Sorry, excuse me, BMC or BXC? Do you mean BXC? Because
BXC, yeah, sorry, yes. BMC, this guy. BMC. This triangle is congruent, is similar to the triangle ABC because they are sharing the same angle, C, and the other one is dot 1 is the same as dot 2.
Yes,
so these are the two triangles. Yeah, any question, just let me know. Okay, so let's continue. Now you see these two triangles are similar to each other. You're going to have what? BC squared equals to MC times AC, right? MC is 1, AC is 2. So therefore, BC equals to root 2. Okay? You don't have to do anything. This is a conditional react. It might be useful, it might not be useful, but it won't take too much of time, right? Every single problem, if you think from the very beginning, it's going to take forever. But if you have a lot of conditional react, you very mechanically give all the segment measurement, all those values automatically, it's going to save you a lot of time. Okay, my first conditional react is try to use the similarity we talked about. This conditional react number 1. Conditional react number 2 is pretty much as long as you see the angle bisector, you're going to use the angle bisector theorem, right? This is what we talked about from day 1. Angle bisector is going to use the angle bisector theorem. Okay, in this problem, which one is the angle bisector? This guy, right? This guy is the angle bisector, CN. Okay, this CN is an angle bisector actually for two triangles. One is this gray triangle BMC. The other one is the big triangle ABC. Is that right? So which one I need to use? Which one is useful? Which one's not useful? Like I said, make it very mechanically. Just write it out. You don't have to think too much. You just mechanically write out. In triangle BMC, gonna be BC, MC, BX, XM, right? In triangle ABC, is going to be BC, AC, BN, NA. Okay, I don't know which one is used for which one's not. I'm just like randomly random out. I just basically random out. Okay, let's have a look at BC over MC. I already know the calculation for BC. So this is going to be root 2. BX over XN is root 2. The other one, BC over AC. BC is root 2, AC is 2. So this is root 2 over 2. Okay, this is very mechanical. I don't think too much. BX, XM, okay. BN, NA. Don't forget, BX, BN. They are pretty much the same thing because they are the two sizes of your equilateral triangle, right? BX equals to BN. Okay. Now, the question asked me to determine BX. Oh, it looks like I'm kind of in a good track, right? I already have BX, I already have BN, I have a bunch of relationships, and the question is really asking me to determine side of the equilateral triangle. But there are some relationships between here, you know, BX, XM, BN, NA, and I know BX is actually equals to BN. You know what? Because the equilateral triangle has the three sizes are the same, maybe I can try to do some quick replacement. So let's say if BX and XM, the root 2 relationship, so this is going to be A. I'm going to use the color maybe green, okay? So my XM is A. My BX is going to be root 2A, right? Which makes sense. So this is going to be root 2A. This is going to be root 2A. And then what about my NA? My NA is going to be equals to root 2 of BN. So NA is going to be 2A. Oh, now I see something more straightforward. I have a triangle. So it looks like the majority side of my triangle could be either calculated out using root 2, 1, 1, or they can be represented using A. Could be A, root 2A, 2A, like whatever. And my goal is to determine BX, which is root 2A. So the $1 million question is, how can I determine the root 2A, or even just A? You see, I have already used my conditional react. I write out all the segments with all those denotations. And my goal is try to determine the value for A. Try to determine the value for A. I kind of an equation, right? It's a one variable. I just need the one equation, and then my work is done. And the $1 million question is, how can I find this equation? How can I find this equation? If you recall what we have introduced, there are two very important theorems. One is the angle bisector. That's pretty much we have already done. And there's another theorem, like I said, almost test every single year. Somebody mentioned Stewart. Yeah, Stewart is a perfect solution, but Stewart is going to be too lengthy. You're going to do a lot of calculations. Can I do a very easy theorem? Not as complicated as Stewart. I will be able to solve the problem in no time. There's a one theorem, like I keep saying, it's going to be used every single way. Pythagorean? No, there's no right triangles here. You can't use the Pythagorean. Paul, how can I do that? I see Paul has the correct answer.
Cosine law and triangle AMB and BMC.
Exactly. You just use the cosine law, right? Like I said, cosine law is your kind of your number one rule. You don't have to use it every single time, but that's your number one rule, right? As long as you got confused, I don't know what to use, cosine law. You just directly use cosine law in the A and B, one triangle, you're good to go. This triangle has all the sizes presented using A or number 1, like whatever. And then you know this guy is actually what? 60 degrees. So therefore, it's very easy for you to use the cosine law. Use cosine law in triangle ABM or BAM. Okay, so your cosine angle ABM, which is cosine 60 degrees, will be equals to 2 plus root 2a perfect square, root 2 plus 1a perfect square minus 1 square, 2 root 2a times, the calculation is a little bit nasty, but it's a very easy peasy thinking process. You don't really have to think too much, right? And then you list out an equation for this cosine law. Cosine 60 degrees, 1 over 2. You just have to solve this equation, one variable equation. Yeah, you might have some time doing some calculation, but you'll be able to get the value for A. And the question asks you bx squared is actually 2a squared. It's going to be 10, 6 root 2 over 7. That's pretty much the solution for such a problem. You see, a quick recap for this problem. First, you need to have a conditional react. As long as you see something, don't think from the very beginning. You need to use all the patterns we have introduced. Where to find a similarity, where to find this angle bisector theorem, list out everything that you can list out. You might have to use them, you might not have to use them, but listing them out, sometimes the solution will basically speak for themselves. And then don't forget, as long as you see the angle bisector theorem, as long as you see pretty much nothing to do, think about the cosine law. These will be working together, help you solve a lot of problems. Okay, this is our question number 1. Okay, it's an AMC problem, question number 24. If all good, let's go to another problem from AIME. Try to see if we go to AIME, the policy changes, or they're exactly the same. Second problem, let's go for an AIME problem. Okay, second problem, we're looking at a problem that comes from 2015 AIME 1, question number 11. Okay, question number 11. The problem says triangle ABC has positive integer side lengths. Oh my God, positive integer side lengths. As long as you say this, because a side length does not have to be a positive integer. They can be a fraction number, it can be whatever. But as long as they give a positive integer side length, most likely you're going to use some number theory related discussion, doing some factorization, doing some enumeration, so on and so forth, right? You need to have, whenever you read a question, you need to always have the action word, the signal word. This, whenever I see this, I'm going to do this. Whenever I see that, I'm going to do that. So do not always think from the very beginning. You have no time. A triangle has positive integer side lengths with AB equals to AC. Okay, this is a isosceles triangle. Let I be the intersection of the bisector of B and C. Okay, intersection between two bisectors. Suppose BI equals to 8. Find out the smallest possible parameter of triangle ABC. Again, let's give the graph. It's something like this, I guess. Here you have an isosceles triangle. You have something just like, maybe something like this, like this, like this. Okay, you have a triangle A, B, C. Okay, so you have AB equals to AC. Okay, these two guys are the same. And you have I be the intersection between the bisector B and C. So this is going to be your I. Okay, if BI equals to 8, find out the smallest possible parameter of your triangle ABC? Well, try to find out the smallest possible parameter of triangle ABC. You have to know the two sizes, right? I'm going to say this is maybe A, this is A, this is B, right? So because I is the intersection between the two bisectors, it's going to be the in-center, right? So this is going to be B over 2, right? I know this is going to be 90 degrees. That's some basic stuff. So first thing first, what should I do? I have blah, 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 angle bisector. Okay, as long as I see the angle bisector, I'm going to do the angle bisector. Angle bisector. I'm going to use the angle bisector theorem. Like I said, I don't know it's going to be useful, not useful, but I'm just going to use it. Okay, it's going to be what? AI ID equals to AB B. I have a given name D here, BD. Okay, so that's going to be A over B divided by 2. Okay, and because I know A, I know B over 2, and I know AD. So using the Pythagorean, AD actually equals to A squared minus B squared over 4. Okay, I know the value of AD. Okay, I know the value, the total value of AD is under root A squared minus B squared over 4. And I know AI over ID is A over B over 2. So basically, I can find out the value for ID. ID is going to be A squared minus B squared over 4 times B over 2, A plus B over 2, right? It's actually that portion of this entire AD. Okay. So my goal at the end of the day, I need to determine the smallest parameter of triangle ABC, basically A plus B, the minimum value, right? I basically want to do something like this. There are two variables. I think I need to find out a relationship between these two variables. I can't handle two variables side by side, right? I want to make sure if they're the same thing, or they have some relationship. So who can tell me, is there a very easy way to build up a relationship between A and B? Is there any condition I didn't use yet? I didn't use this, right? This guy. BI equals to 8. Is there a quick way for me to kind of using this 8 to squeeze out the relationship between A and B? Steward? Okay, again, steward is too much. Steward is pretty much your last option. As long as you have nothing to do, steward. But I think I have something much easier than steward. Look at this. Check it out here. This is a what? Is there anything I can basically do some easy stuff within this green triangle to find out? Because at the end of the day, I want to have some relationship between A and B, right? If A and B, they're 2,000 miles away, there's no relationship. I have to deal with two variables. But if they can build up some relationship, I'm just going to deal with one variable. That's it. Is there anything? ID is my stuff here. I just get that the value of ID is a nasty value, but kind of having some A, having some B here. Who can tell me? Jerry? Who can tell me? Yeah, I think Jerry has the correct answer. Using the Pythagorean, that's it, right? You can use the Pythagorean theorem within this green triangle. You have 8 square equals to B over 2 square plus ID square. This is a very easy way. You can use steward, but that's going to be your last option because steward is too complicated. You know what? Plug in the value. Plug in here. Do some quick manipulation. A equals to 64B b squared minus 128. Okay? You have this. Okay. Like I keep saying, you know what? Don't be panicked. As long as you see some relatively complicated expressions, no worries. Let's move on. Let's move forward. You might find a very quick solution in about 2 minutes. So now I have A equals to a weird example of B, and I need to determine 2A plus B, minimum value, right? Okay. So one way is I just basically plug in the value, right, into this expression, 128b, b squared minus 128 plus b, and then do the algebra way to find out the minimum value, so on and so forth. Of course, you can do that. But wait a sec before we move forward. There's a very important condition I didn't use yet. What is the condition? Go back to check the question. I want to determine the value of for 2a plus b, but a and b, they're random numbers, or there are some certain specialties for a and b. Luis?
They're integers.
Yes, integers. Don't forget, they're integers. Okay. If they're integers, maybe, you know what? If you're very common with the math competition courses, as long as you have integers, and I give you this weird relationship, most likely you have two approaches. One approach is you find out A times B equals to another number, and then try to do the factorization, right? But you have to put A and B to one side of this equation, and the numbers on the other side. But in my expression, you won't be able to do that because you have a bunch of A on the left, bunch of B on the right. Or alternatively, if I can find a range of B or A, like whatever, let's say, because B is an integer, if I can say B is between 3 and 5, the only integer between 3 and 5 is actually 4, right? We can just use 4 to plug in to the original expression, try to see it works or not. Either way, these are either way correct. Well, the only difference is that if you can put all the A and B into one side of the equation, do this one. This one is more direct. Just do the enumeration, that's it. But if you can't, like in our problem, you can have some of the A here, some of the B here. They cannot be all on the same side of this equation. Maybe you're probably going to go for the second one. Either way, you can try them both. Right? In our number theory part, we talk about this too much. So let's try to see if there's anything I can deal with inequalities perspective. Try to find out some range of A or of B, so on and so forth. Let's have some quick look. This is not a magic. It's fairly understandable. You see, we are looking at a isosceles triangle, right? AKA these two guys. They're the bottom angle. So of course I know that angle 1, let's say this is angle 1, this is angle 2, this is angle 3, this is angle 4, give me an example. Angle 1 plus angle 2 equals to angle ABC must be lesser than 90 degrees. Of course, isosceles triangle, the bottom angle cannot be an obtuse triangle. So therefore, you can have angle 1 must be lesser than 55 degrees, right? Similarly, angle 4 must be also lesser than 35 degrees. And then that being said, if I focus on this triangle, you have two bottom angles are lesser than 35 degrees. So your angle BIC must be greater than 90 degrees, which makes sense. So that being said, your BIC is actually going to be an obtuse triangle. Okay. Obtuse triangle. I want to find out some range for B. Let's have this. BIC. This is B. This is 8. This is 8. This is more than 90 degrees. If BIC is equal to 90 degrees, B is actually equals to 8 root 2, right? This is going to be a right isosceles triangle. But BIC is greater than 90 degrees. So angle B will be greater than 8 root 2. This is understandable, right? If B is greater than 8 root 2, so I kind of having the range of B. Plus, B is actually within the triangle BIC. If I want to find another inequality relationship, like I keep saying, this is our rule number 1. If you really have nothing to do, you want to find out an inequality relationship, the best one is B is lesser than 8 plus 8. The intrinsic relationship within the triangle, right? So therefore, B is greater than 8 root 2, lesser than 16. Now you see a range of your B. Okay, some students say, I might have an even more flowery calculation. I can give you an even smaller range. Oh, well, good for you, right? But here's like a balance, right? You don't want to think too much. Thinking is very expensive, right? You think too much, you spend a lot of time, you get a relatively smaller range, but so what? Because you just have a range. This is 11.313 something. There are not so many numbers for the range. These are pretty much 4 numbers for B, right? You can do a lot of calculation, having a lot of smaller range, but it doesn't matter. You just have 4 numbers. Try them one by one. Having this B number, plug it into this A, find out A must be an integer, right? If A is not integer, just forget about it. And then do the calculation one by one. Find out actually when B is 12, A is actually 48. And then the parameter 108 is the minimum parameter that you can calculate. That's it. You try 13, 14, 15. Sometimes A is not a prime. Sometimes A is not an integer. Sometimes it can have a larger value. But nonetheless, you will be able to see such a thing. This is the thinking process, right? I think it's very important. So far, so good? Okay. So this is actually our second problem, talking about how to use this. You know, as long as you see the angle bisector, it's like so important. Using the angle bisector, you'll be able to have the angle bisector theorem. And taking from there, these are all very mechanical stuff, right? These are more number theory related discussions. So always, as long as you see the angle bisect, use it right away. And then just move forward using your conditional react. And then you'll be able to do the problem. I think 2 problems, one from AIME, one from AMC, is good enough to tell you the importance of using the angle bisector. All right? If all good, it's time to go to our second category. The second category is, let's try to say something about similar triangle. Most important thing is the area ratio is the similarity ratios for fixed square. I'll start a very easy even problem. 2, there you go. It's easy peasy even problem. It's a problem from 2017. AMC12B, question number 18. So the problem says you have a circle. This one is very easy. I'm just going to give you the answer right away. You have a circle. Within the circle, you made a diameter. Okay, here. Yeah. You have a diameter AB of a circle with radius 2, 1. It's extended to the point D, such that BD equals to 3. Point E is chosen such that ED equals to 5. And DE is perpendicular to AD. Segment AE intersects the circle at point C. And between A and E, so what's the area of the triangle ABC? What's the area of this triangle ABC? This one is like so easy, right? Because this guy, I think pretty much all the students can solve that in about 20 seconds. Question asks you to determine the area. And then you see similarity right away. Yes, I'm gonna maybe I'm gonna ask some students to tell me. Erickson, you wanna tell me how to do such a problem?
It's inscribed in a semicircle, so they're similar with a ratio of 2/5. The area of the big one is 25/2.
Yep.
And then you just multiply by 4/25.
That's it, right? Exactly. Because you find out triangle ABC is similar to triangle AED. So the area ratio, area of ABC over the area of AED will be the similarity ratio's perfect square. Similarity ratio is fairly easy. You can find out this guy is actually under root 47 using a Pythagorean. So this is going to be 4 over under root 47, perfect square, right? And the area of AED, you can basically plug in the value, right? 7 plus 5 times 5 divided by 2. So the area of ABC is actually 140 over 37. This is like a given, right? You must do this problem within 20 seconds. Calculation, so important. Make sure you don't make any mistakes. As long as you see two triangles, they're congruent, they're similar to each other, automatically using the similarity ratio, perfect square, it's going to be equals to the area ratio. This is extremely important. Okay, this is given, right? I don't want to say too much, but let's go for another problem. You can find out, I'm going to give you an AIME problem. You can find out the similarities perfect square equals to the area ratio is not just for triangles. It could be applied for any shapes. As long as they are similar to each other, you can apply the property right away. So second problem, I'm going to give you an AIME problem. This is a problem that comes from 2010, AIME 2, number 9. It's a different problem, but exactly the thinking process. Let ABCDE be a regular hexagon. I'm going to give you the graph because this is, you need a regular hexagon here. Okay, it's going to be here. Okay, you have a regular hexagon, A, B, C, D, E, F. You want to give the median. Let G, H, I, J, K are the median of different 6 sizes. I'm going to give you the median, okay? I'm going to write it here, 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 okay? The segment AH, okay, goes like this. AH. The other one is BI. I'm going to keep this. This is J, G, H, I, J, K, L. Okay, the segment AH, BI, what's next? CJ. Next one, DK. Next one, EL. Next one, FG. Okay, they're actually bounding out a smaller regular hexagon. You see? The middle one is actually also a hexagon, but it's like smaller. Right? This is a smaller hexagon. Okay, which makes sense, right? Just gonna highlight it here. Okay, the smaller hexagon is also regular. Let the ratio of the area of the smaller hexagon to the area of the big hexagon, ABCDEF, be written as m over n, where m and are relatively positive integers, find m plus. And this is a typical AIME way to ask you, right? They don't want to really give you the value m plus n, and then they want you to basically write like m and n, the two values, adding them together. So basically what you need to do is you need to calculate the area of the small, the area of the big. What's that? What's the ratio between the small area and the big area? As you can see, small hexagon must be similar to the big hexagon. All the hexagons there are similar to each other, right? So this must be the similarities ratio's perfect square. So my $1 million question is, if I can find out the similarity ratio between these two shapes and then make a perfect square, my work is done. How can I do the similarity ratio between the two? Well, to do the similarity ratio between the two, you need to basically find out either the same side, right? Or the corresponding side. So here I want to give you guys a quick heads up. Let's say if I have two triangles, they're similar to each other. So these two guys, their ratio will be definitely similarities ratio. Or instead of having the side ratio, if I can find out the corresponding segment, you see the two height, right? The two heights ratio is also the similarity ratio, right? So you don't have to be really find out the what should I say? Really find out the side ratio, because it's not easy, because you see like the green one is like tilting there. It's not easy to find one of the side. But if I can find out some corresponding sides ratio, I can also do the work. How can I find the corresponding side? This is the $1 million question for such a problem. Okay, I'm going to give you a hint. Let's say I find out the center of my hexagon. So this center will be shared between the big one and the small one, right? Okay. One way is that I'm going to make a connection. I use the color maybe red. Connection between OH, give a name O. The OH is kind of perpendicular to BC, right? It's kind of like the height from the middle, whatever. And then I'm going to do the same thing. I want to make a height to this guy as well. I'll give a name, maybe M. OM is perpendicular to my AH. So OM is perpendicular to AH. OH is perpendicular to BC. So that being said, if I can find out OH over OM, this is also considered to be similarity ratio. Does it make sense? Does it make sense to you guys? Because they're all height. As long as I can find out the height ratio, I can also solve this problem. Does it make sense to you guys? So now the $1 million question is that, how can I find out the ratio between this OH and OM? To do the OM might not be that much easy. Let's think about it. But maybe it's easy for me to do the OH. Who can tell me? Is there a very easy way to determine OH? Is there an easy way to determine OH? How can I get a value of OH? Somebody mentioned, can I set OH equals to 1 without the law of generality? Yes, you could. Yeah, of course. You can do that. Or maybe I'm going to do something you like, because we have so many midpoints here, right? G, H, I, J, K. I'm going to say this hexagon actually has a side length equals to 2. So I want to make sure they're all integers all over the places. If that's the case, how can I find out the value for OH? It's actually fairly straightforward. You know what? I'm going to give you a hint. Do a connection between OC, and you find out everything within this triangle. Is it easy? Because hexagon, right? Regular hexagon, everyone will be 120 degrees for the angle. So you'll be able to basically create a triangle. Yeah, just like Tracy mentioned, you'll be able to find out the value for OH. Who can tell me what's the value for OH? Who can tell me the value for OH? Tracy?
√3.
That's it. Fairly easy, right? This is not a rocket science. So I get a value for OH, √3. So my next one is I need to get a value for OM. Well, to get a value for OM is not really touching too much, right? I have to put it into a triangle. Like I keep saying, triangle is the most important thing. Everything needs to be done within a triangle. So this time, I'm going to give you a hint. Let's try to do your magic. Focus on this triangle. Can you see how you do the problem within this triangle?
AO equals OC. OC we can also get, right? That's 2.
Right?
And then we can get and then we can solve for do we have AH or can we
That's a $1 million question. Yes, you need AH, but how can I do AH?
we have quadrilateral with sides 2, √3, 2, 1, and 2, right?
Yeah, I think you're in the right direction, Alan.
Connect OB. I think that will be 2, right?
OB?
Oh, yes, because, yes,
yeah,
of
OB
course,
is 2.
OB will be 2.
I think, yeah, you have very nice direction. I think you need to focus a bit more in this triangle, right? This triangle, you have
20.
Here, A, B, H.
Oh, I can use cosine rule, right? Cosine law to find.
Exactly.
Yes.
Like I keep saying, cosine law is your friend. You always have to remember cosine law, right? Whenever you have nothing to do, think about the cosine law. Using the cosine law, you'll be able to determine AH. Cosine law. AH is equals to what? √7. Okay? As long as you know √7 within the red triangle, you already know the 3 sizes. And OH. OH is actually height for the bottom AH.
Oh,
you can
2
use
times √3 equals AH times OM, right?
You can, oh yeah, there are so many ways. Yes.
Okay.
To
Yes.
determine OM, you can actually do this. AOH, right? This is √7, this is 2, this is √3, this is 90 degrees. You can basically, using the Heron's formula, determine the area, and then using the height times the bottom. You can even use the double angle, what is called the double Pythagorean theorem we introduced in our lecture, try to do the calculation. But nevertheless, there are different ways to do it. You can pick up the one you like. Having a triangle, 3 sizes given, just want to ask you one of the height. It's fairly straightforward, right? So our OM can be determined as 12/7. Easy. With all those information together, you'll be able to find out, okay, these are the similarities perfect square. Like the similarity ratio's perfect square is going to be equal to your area ratio. And this problem is going to give you 4/7. You see, It's a very understandable process, nothing too complicated. As long as you always have this in mind, similar triangles, their side or their corresponding length, perfect square ratio is going to be equals to the area ratio. You can always solve the problem. It's fairly quick. Okay, so this is actually our second problem. Try to remember, see, it has nothing to do with it's a triangle or it's a quadrilateral or it's a hexagon. The thinking process are exactly the same. Okay, this is actually our second category. If all good, let's go to our third category. Our third category is actually using trigonometry to do geometry problem. So I have two problems. The first problem, I just like to give it to you and you guys can think about it offline because I think this problem is fairly easy. This is a problem from, you see the year, is 2014. 2014 AMC 12B, question number 21. And this problem is exactly the same as 2018 Euclid, question number 8, B part, exactly the same thing. If you use the official solution from Euclid or from AOPS, it's very time consuming. You're gonna do a lot of heavy calculations here and there. Still, you're gonna have it, but try to think the trigonometry way. You can have a very quick solution for this. It's gonna save your time significantly. Think about it as a homework. And then if you have any questions, you can let me know because I think we talked about this question many times. So I'm just gonna skip it. So this is a typical problem that I like everyone to know. Using the trigonometry can solve the problem so much. I'm going to give you another problem. I'm going to give you a relatively difficult problem because the more challenging the problem is, the more beauty you're going to see how we're going to use trigonometry to expedite the calculation process. So the problem I would like to give you guys to do the demo here is a problem. I'm going to give you here for the library. Number 3. I want to give you the second one. This one is a problem that comes from 2010 AIME 1, question number 15. The last problem from AIME. If you go for the algebra way, that's going to kill you. But if you want to go for the geometry, like the trigonometry way, it's going to really help you to expedite your calculation process. Let's have a quick look. I have a triangle. The triangle, I give you the 3 sizes. Do you remember? As long as you see 3 sizes of a triangle, what do you have to do? Your conditional react. What do you have to do?
The cosine.
Not a cosine law before that.
Or
You
check for 13. Check for triples.
Exactly. The Pythagorean triples. But unfortunately, they're not Pythagorean triples. It's always good to check. It won't take you too much time, right? But if it is right triangle, your work can be so easy. You have a triangle, and let M be a point on the AC such that the yin circle of triangle ABM and the BMC have equal radius. Okay, 2 yin circles have the same radius. And then AM over AP equals to AM over CM equals P over Q. Then P and Q, the relatively prime numbers. Try to find P plus Q. First thing first, let's have a graph. And a graph, I'm going to give the color to black. Here's this, goes like this. Okay. And you have a point here. Yep. And from here, you have here, here, here. And from here, you have maybe here, here. Yep. Okay. So here's the thing. You have a triangle A, B, C. Okay. And you have AB equals to 12, AC 13, BC13, AC15, okay? You have an endpoint here. This endpoint is chosen such that ABM triangle and BMC triangle, they have the same, like the inscribed circle, they have the same radius. Okay, I'm gonna give maybe this is gonna be my P, this is gonna be my Q. So they have the R, right? R. Okay? And with all those information, the question asks you, what is the measurement for AM over MC? Oh my God. AM over MC. They are actually in the middle of nowhere. How can I do this problem? Well, we have to see what we have, right, at the very, very beginning. Well, this problem says you have a triangle cut into two parts. Left-hand side, you have 3 R's. Right-hand side, you have 3 R's, whatever. And if I know this is a inscribed circle, so I know that this is going to be, give you an example. This is going to be alpha. This is beta, right? Okay. My goal is to determine AM, MC. AM, MC. Well, I really do not have too much information to get started, right? I can't put them directly into a triangle. I cannot really do too much stuff. Okay, who can tell me, like I keep saying, as long as I get lost, I have nothing to get started. What is the only rule I can use for a triangle? I have nothing, right? I only have a bunch of like inscribed circles, that's it, some radius. What is the only thing that I can start it with? Whenever you have no rules, no laws, what is the
I'm sorry, how did you find the angle bisector?
angle bisector? Because it's the inscribed circle. Inscribed circle, it has the same, right?
Okay, sure.
Is it like angle bisector? That doesn't make sense?
Yeah, I understand. I just
Yeah,
didn't.
sure, no problem. Yeah, any questions, just let me know. Yeah. If I have nothing to do, what is the only thing that I can start with? Like I said, I don't really have too much information. I only know 3 sizes. I think there's only one thing I can get started with the 3 sizes. What is that? Yeah, somebody mentioned Harris formula for sure. Harris formula, yes, brilliant. What else? Since I already marked out the angle thing, what is the only thing that I can do with nothing, right? I get started with nothing. Gabriel? What is the only thing that we can do?
Law of cosine.
Cosine law, right? Exactly. The only thing I can do is the cosine law. Okay. But cosine law, I'm going to have a calculation. Cosine 2 alpha equals to what? 4 over 9. 5 over 9. Cosine 2 beta. Cosine 2 beta is going to be equals to 25 equals to 39. Right? This is not a magic, right? But after I get this, cosine 2 alpha, cosine 2 beta, but I think in my following discussion, if I want to determine, for instance, if I want to determine my AM over MC, I pretty much want to do maybe AP plus PM, something like QC plus MQ, something like that, right? It might be pretty much what I want to do. But whenever I want to determine this AP, I probably want to use just one cosine, just alpha, right? Not 2 alpha, just 1 alpha. Could be tangent, could be cosine, I don't know. At least I'm not using 2 alpha. Same thing, whenever I try to determine my QC, I'm probably just going to use 1 beta. I don't know, tangent, the cosine, like whatever. So my $1 million question is, now I have 2 alpha. But I want to use alpha eventually. I have 2 beta. I want to use beta eventually. What kind of rules, trigonometry rules, can help me do this conversion? Who can tell me? From 2 alpha to alpha, sine, cosine, tangent, cotangent. I don't really know what I need to use, right? But who can tell me what is the most important rule help me to reduce from 2 alpha to alpha? So whenever you use the trigonometry to solve the problem, you better have some trigonometry knowledge, right? I'll ask for Phyllis.
Use the half angle identity or double angle identity.
That's brilliant. Half and double angle identity, right? That's brilliant. Well, the good part of that is it's nice, but I'm gonna have maybe a cosine alpha, cosine beta bunch of stuff. I think there's another rule also help us reduce from 2 alpha into alpha. But I won't have too much sine, cosine, blah, blah, blah. I can have use one identity, one trigonometry, and do everything. Do you guys know that? Because the thing is that I do not want to have too much variables, right? If I use the half angle, the cosine 2 alpha is going to go to maybe a sine, cosine, right? Sine alpha, cosine alpha, blah, blah, blah. If I use the cosine, maybe I'm going to change it to tangent. It's just too complicated. Is there anything I can just consolidate all my cosine alpha stuff, cosine 2 beta stuff, just into one easy peasy expression? That's the famous tangent half angle formula. Do you guys know this? Tangent half angle formula. It means that all your sine 2 alpha, cosine 2 alpha, tangent 2 alpha, they can all be converted just using tangent alpha. Just using tangent alpha. Do you guys know this? Can I have a quick survey? Have you guys learned that? Tangent half angle formula. We introduced that in our regular lectures, but if you come from the other lectures, the other things, maybe you never heard about it, right? Yeah, it's okay. We're going to talk about it in our upcoming session. So today is like lecture number 1. So we just basically talk about it, give you guys an idea. But this is extremely important. Tangent half angle formula can actually save you a bunch of time. We can even, in Chinese, we even call it 万能公式, means you can do anything you like. Of course, you won't do anything, but just show the being powerful of such a thing. As long as you know this, a lot of complicated things can be converted directly using tangent alpha. You convert a complicated, trigonometry thing into some easy peasy calculation. Okay? So that's the reason we all know this cosine 2 alpha, cosine 2 beta, blah, blah, blah. Let's try to convert it into tangent alpha, tangent beta to make our life easy. So cosine 2 alpha will be equals to 1 minus tangent squared, 1 plus tangent squared equals to 5/9. So tangent alpha equals to √2, √7. Cosine 2 beta equals to 1 minus tangent squared beta, 1 plus tangent squared beta, and 25/39. So therefore, tangent beta will be √7 for √2. Okay? Okay, let's have some quick look at it. This is my alpha, right? This is my beta. I want to find out some relationship. Now I find out, okay, tangent alpha equals to this, tangent beta equals to this, but there are so many segments there. I want to find out the relationship. Actually, I find out, let's try to focus on this two guys. This is a right triangle. with tangent alpha. This is a right triangle with tangent beta. I know the value for tangent alpha and tangent beta, right? So that being said, maybe I can do something like this. I'm going to use tangent alpha over tangent beta. Why? Because you see, I'm actually sharing the same, like my opposite side is actually sharing the same, right? And you can see that, hey guys, can you guys hear me? Hello, can you guys hear me?
Yeah.
Okay, yeah, I think there's something wrong pops up. Okay, so, okay, let's continue. Okay, so tangent alpha and tangent beta. Let's try this, because why? Because tangent alpha equals to R over AP. Tangent beta equals R over QC. And two R's can be canceled, right? That's going to be my CQ over AP equals to this two tangent thing, 7, 8 over 7. Because my goal is try to determine the value for what? AM, MC. I don't really care this R thing, right? R is inside. I more care about this side length. So QC and AP, they are actually having 8 to 7 relationship. Okay, you know what? Let's try to make my life easier. I'm just gonna let CQ equals to 8x. AP equals to 7x. Let's have a look at it. What's gonna happen? CQ is 8x. AP is 7x. So this is gonna be 7x as well, right? So this part is gonna be what? 12 minus 7x, because the total sum is 12. This is 8x. This is also 8x, right? And this part is going to be 13 minus 8x. Okay. If this is like 8 here, 12 minus 7x, this is also 12 minus 7x, right? If this is 13 minus 8x, I'm going to highlight it here. So this part is also going to be 13 minus 8x. So that being said, it's going to be 1 minus x. Does it make sense? Because they share something in between, right? So the little one here, if I use the color yellow, should be 1 minus x. I think this is understandable, right? Well, the other two things, I want to determine AM over MC. There are two more things here. This is M. This is N. Because I really have no idea how they are, right? Now, you know what? I might have some information. Let's have a quick look at it. First, if this is M, this is going to be M, right? If this is N, this is going to be N. So U minus X equals to M minus N. Makes sense, right? Okay. Second, we talk about this M thing a lot of time, right? So what I say, my tangent X, right? This is X, 7X, 7X. Okay, so you know tangent X, right? Tangent alpha. Tangent alpha, you tell me, actually equals to R minus AP. R minus, yes, R minus AP. Mar or AP. R, I don't know. AP is 7x. So this guy actually equals to what? Tangent x equals to √2 over 7. Okay, let's continue. Let's continue. I have 7x plus m plus n plus 8x equals to 15. Okay, you see, I have 1, 2, 3, 4 variables. I have 3 equations already. I just need an extra equation. As long as I have an extra equation, I would be able to solve the problem fairly quick. How can I find out my last equation? This is the only tricky part for this problem. Now you have 3 equations, right? This 3 equations is very understandable. But how can I do the last equation? Let's check it out here. This is the only tricky part. For this quadrilateral and this quadrilateral, let me see a few things. This angle is actually the same as this angle. Does it make sense? Any objections? These 2 angles are the same because they both plus like angle AMC equals to 180 degrees. So these are the same. Similarly, this angle is the same as this angle. These 2 green dots are the same. So AKA, these 2 triangles are actually what? Similar to each other, right? This is the tricky part. These 2 triangles are actually similar. These 2 quadrilaterals are actually similar to each other. So I'll say the red is similar to the yellow. If they're similar to each other, you're going to have R over M equals to N over R. R over M, for one triangle, R, M, and R. Corresponding sides are proportional to each other. This is the tricky part for such a problem. Now, you have 4 equations. You have 4 variables. This is not an easy problem. It's AIME question number 15, right? So you have to do some calculation. But 4 variables, 4 equations, you can definitely find out an equation. Actually, you can find out x could be equals to 2 over 3, or 2. It's going to be the equation. You want to cancel the x, right? Fine. So you want to cancel all the variables, find out the value for x. But I have 2. One is 2 over 3. One is 2. Which one I need to take? Which one I need to take? This is, again, a little bit quick thing. You need to do a quick analysis. Because, let's check out here. Let's check out here. Your ace equals to 15 equals to 15x plus m plus n. From here, you can find out actually x must be lesser than 1. If x is greater than 1, then m must be negative, right? So therefore, you need to remove the 2 part. See, this problem has some little tricks here and there. You have to overcome all the tricks to have the correct answer. So therefore, x equals to 2 over 3. If x is equal to 2 over 3, it's very easy for you to determine the value for m, for n. You just plug in, figure out all the values. So at the end of the day, you have am over cm equals to 22 over 23. That's the solution for such a problem. You see, this problem could be very challenging. Even, trust me, because you use some trigonometry, you reduce the complexity. If you just directly go for the algebra way, like the typical, what should I say, the area method, trust me, this is going to be this is going to, oops, what's that? I close it. This is going to be a nightmare. You can find out this is going to be a nightmare. However, using the trigonometry, you actually convert all those complicated calculation process, dump them into the trigonometry calculation. You can expedite your calculations significantly. And trust me, the same thing for the previous problem I mentioned. So this, like the first problem, 2014 AMC12B, question number 21, this is also the same thing. If you're trying to use the typical algebra plus geometry way, it's going to take forever. But using the trigonometry solution, it's going to expedite your calculation significantly. So far, so good. All right. If all good, let's go to the last category of today's lecture. We're going to talk about in the circle. You always want to use something like the, like the cyclic, or you want to talk something about the like the Ptolemy. So these are actually very common from time to time. Having a good understanding for this is really going to help you to expedite your calculation process. Okay, let's have a quick look. I'll have two quick problems for you. The first one is a problem from 2011, AME2, question number 10. The question says, a circle with center O has a radius 25. Okay, radius 25. Chord AB of length 30. Chord CD of length 14. They intersect at point P. The distance between the two midpoints of the two chords is 12. The quantity OP square can be expressed as m over n, where m and their relatively prime positive integers. Find out the remainder when m plus n is divided by 1000. You need to have the nice graph. As long as you have nice graph, all those problems will speak for themselves. You have AB equals to 30. You have CD equals to 15. You have the two meet connection. Okay, so A, B, C, D, E, F. Okay, AB is 30. AB 30. CD is 14. The two meet connection is 12. The question asks you to determine what's the value for OP square. This is P. This is O. This is O. Okay. How can I determine this? Well, I think the good part is before we get started, I think everything that you know is I know how to determine the distance from my circle center to the chord. This part I know, right? As long as you give me a circle, let me change the color to maybe red. You give me a circle center, you give me a chord. I know the length of the chord. I know the radius of my circle. I will be able to determine OE and OF. Do you have any objections for that? Obviously, I know OF equals to 24. OE equals to 20. Do you have any objections? Can I ask your opinion? Are we all good? Yes or no? Are you there? Yes or no?
Yeah, that makes sense.
That makes sense, right? Okay, student know how do you get it? Yeah, it's okay. If you don't understand, I can give you a quick explanation. You have a circle, you have a chord, you have a connection here, right? You want to know how to determine this. This guy is This is A over 2, right? This guy is R. So using the Pythagorean, you can basically determine this. This is so easy. Try to remember, this is very important. Okay. Okay. If all good, the next part is how can I determine this OP stuff? I know OE, I know OF, I know EF. This is what you told me. And how to determine OP. Okay, I think Paul has some ideas. Yes, Paul, you want to say something?
Use Ptolemy's.
Use Ptolemy's? Okay. Use Ptolemy's, you probably have to figure out what's the value for this. What's the value for PF? What's the value for EP? How can I do that?
Pythagorean theorem.
Pythagorean? Huh? Yeah, that's a good idea. Using Pythagorean, then you'll be able to get pretty much everything, right? Okay, we already find our first solution. Solution number 1. Ptolemy. Because your triangle is cyclic. Is it right? You have 290 degrees. Then you directly using the Ptolemy. Ptolemy will be able to have what? OP times EF equals to EP OF plus PF OE, right? OP, you don't know. This is what the question is asking for you. EF equals to 12. EP can using the Pythagorean theorem. You can actually calculate out, right? OF is actually given 24. PS also using Pythagorean, and OE can actually given 20. This is a brilliant answer. Yes, Ptolemy. You get it, right? What else? What else? Ptolemy is a brilliant solution. Yes. You see, using some Ptolemy sometimes really can help you expedite your calculation. This problem, we can also use another way to solve it, is using the area method. Why? Because you can focus on this triangle. This triangle, what is the OP? OP is the diameter of the circumcircle of this triangle EOF, right? OP is the diameter of the circumcircle of this triangle EOF. So that being said means what? Do you still remember we have an area method? The area equals to what? The area equals to ABC for R. R is the yes. I think Erickson has the answer. Yes, the area of this triangle can be written as ABC over 4 times the radius of this circumcircle. The triangle, I already know the 3 sizes. Determine ABC is given. Determine the area is given using Heron's formula. ABC, you know it. Directly, you find out the value of R. Is that right? If you know the value of R, you can basically determine OP square, which is 4R square. You see, both those 2 solutions are pretty easy. And using Ptolemy, I think using Ptolemy is a very good solution. Yes. Or using the area method. Either way, you can also have a very fast solution of this. Okay. So far, so good. If all good, let's go to our last problem. You see, sometimes whenever you see some difficult problem, but as long as you use the correct formula, you can actually make it so straightforward. You do not really have to do some very, very complicated stuff. You know what? This problem is also the last problem. 1 formula, 1 equation, you get what you need. This is 2001 AIME. For now, it's only an AMC difficult problem. Question number 13. Okay, let's have a look. In a certain circle, right? the chord of a degree arc is 22 centimeters long. You have an arc, right? Degree, and then you have the chord is 22 meters long, 22 centimeters long. And the chord of 2D degree arc is 20 centimeters longer than the chord of a 3D degree arc. Normally speaking, in the circle, the larger arc is going to face a larger chord. But now why a 2D degree arc is even longer than the 3D degree arc? Why? All the way you read to here, you need to ask yourself why. Why? Because you see, in a circle, longer arc, longer chord, bigger arc, bigger chord, bigger arc, bigger chord. But why sometimes you have 3D arc is even smaller than the 2D arc? Paul? What's
3D
happening
is
here?
larger than 180.
Exactly. Because you might have some minor arc and major arc. Is that right? Minor arc means the arc is lesser than 180 degrees. So the bigger arc, the bigger chord. But major arc, this is my major arc. This is actually facing along. For the major arc, even the larger your arc is, actually the shorter your chord is. This is the only tricky part for such a problem. Okay, so the question says the length of the chord of a 3D arc is minus m plus n centimeter. So where mn are positive integers, find a value for mn. So for this guy, I think the most important thing is you need to construct. We use the construction method, right? We have to construct. Okay, a student got a question. May I ask, what is a D degree arc? A D degree arc is something like this. They say this is 60 degrees. So this part is a 60 degree arc. And this is the minor one, right? The major one is this guy is actually a 300 degree arc. That's the definition for an arc. Certain degree arc is actually determined by using the angle, the center, like the center angle facing to it. Yeah. So for this problem, the $1 million question is how can I properly construct out my graph? In this graph, right, have a degree arc, which is 22. You need to have a 2D degree arc, which is 20 centimeters, even longer than the 3D degree arc. This is the most challenging part for such a problem. As long as you have the graph, this problem is essentially given. Okay, how can I have this? I think we don't have too much time. I'm gonna just directly give you this. This is basically how this graph looks like. Okay, you see, I'm gonna have a quick look. We'll see how this one works. We have a D arc. This guy is 22 centimeters. 22 centimeters. 22 centimeters. We have a 2D degree arc. 2D degree arc is already a major arc. 2D degree arc is already a major arc. It actually faces this guy. This is my 2D degree arc. And what is my 3D degree arc? 3D degree arc is here. Is even the major arc. This is actually my 3D degree arc. So this is actually x. This is x plus 20. Same thing. This is also x plus 20. X plus 20. So now, if you want to determine the value for x, What are you going to do? Who can tell me? What are you going to do? Erickson? So easy, huh?
Ptolemy's from here.
Exactly. You directly use Ptolemy's, right? This is actually, you have to use a construction to construct out a very nice symmetric cyclic quadrilateral. And they happen to be the two diagonals are the 2D degree arc. One of the side is the 3D degree arc, while the other three are the 1D degree arc. So you can use AB times CD, AC times BD, AD times BC. It's going to be 22x plus 22 times 22, x plus 20 perfect square. This one is easy. You just basically solve it. X minus 18 plus. You can do some quick simplification. That's basically half minus 9, 165. You see? So that being said, as long as you're doing some relatively difficult problem, you need to remember Ptolemy, you need to remember the cyclic quadrilateral. All those informations are extremely important. Blending them together, and you'll be able to have a very nice solution for this entire process. So that being said, it actually wraps up our lecture number 1. So lecture number 1, we focus on the 2D geometry, pretty much circle and quadrilateral and triangle. Triangle is the foundation, it's the prototype for everything. Circle actually includes all the technology from triangle plus its own Ptolemy, cyclic in order to make it more complicated. In today's assignment, we're going to give you some problems based on those different categories, 4 major categories, and we'll be able to see how we're going to deal with all these problems. And from the next lecture, we're going to go to our second topic, 3D geometry. All right, that's pretty much what I want to say for today's lecture. You have any questions for me? All right, if all good, I wish you guys a good day, and I'll see you guys for the next lecture. Next lecture, we're going to change a different Zoom link. Right, this is for the open course, only lecture number 1. And from lecture number 2, please remember, use our next group. All right, thank you guys. Bye guys, have a good one.